Welcome, welcome, welcome. In this video, we're going to discuss modular arithmetic. So if this is the first time you've ever seen the word modular arithmetic, we're going to introduce you right from the ground up, and you're going to learn a new type of adding, subtracting, multiplying. So I'll start you off with a warm-up problem. Like usual, our videos have a warm-up problem when there's a new topic. So this problem says we have a kidnapper and there are 7 caskets. The caskets were counted in a bit of a funny way. So casket 1 was 1, casket 2 was 2, and so on. 7 was 7. And then the counting started going in the backwards direction. So 6 was then counted as 8, 5 was counted as 9, and so on until they went back down to casket 1, which was counted as 13. The count reversed again, and they went back and forth in this snaking way and counted all the caskets. So the kidnapper claims that you're going to be stuck in this room until you count all the way up to casket 5, 4, 3, 2, 1. That casket will have a key to get out of the room. But if you don't open that casket within 1 hour, then the other 7 caskets will open and you'll die of poisonous gas. So we can't have that happen. We need to open the correct casket. And the correct casket is 5, 4, 3, 2, 1, but there's only these 7 caskets. We have to figure out which of the caskets was counted as 5, 4, 3, 2, 1. So let you pause the video now. Try to think of a way that you can do this, and I'll give you a hint. It has something to do with dividing and finding remainders. So give that a try. Okay, so we'll return to this problem in this video, but we're going to start out with learning the basic must-know details about modular arithmetic. So the story starts with division of integers. So every pair of integers, a and m, you can take a and divide by m, and that will give you a quotient of q and a remainder of r. So q could be any integer, but the r has to be somewhere in between 0 and m, and it could possibly be 0. There could be no leftovers. And we always write it in this way because when we're using modular arithmetic, we don't divide like we'd normally divide in regular arithmetic. There is no division symbol that carries from regular arithmetic to modular arithmetic, but we'll come to that later on below. So for example, if you had a as minus 10 and m as 3, and you're taking a and dividing it up with 3 in each group, then you would have a remainder of 2. Notice that this remainder is always 0 or positive. So minus 4 is the quotient, and 2 is the remainder. Okay, so next we're going to learn the very first symbol that we need to know in modular arithmetic, and that's this congruent symbol that's on the screen right now. It's an equal sign, except there's 3 dashes. This is the concurrent symbol or equivalent symbol that mathematicians use. And it's used for a number of different things. Here we're using it to mean whatever the same thing is in modular arithmetic. So it's like A is the same as B in modular arithmetic. In further detail, we say A is congruent to B in mod M. So what does this mean? It means that they have the same remainder, A and B do, when you divide by M. So A divided by M and B divided by M has the same remainder. Let's write down some examples. So we could say that 25 is congruent to 18 in mod 7. 25 and 18 both have the same remainder of 4 when we divide by 7. You could say 29 is congruent to, let's say, minus 6 in mod 7. Both of those numbers have a remainder of 1 when you divide by 7. You could say 33 is congruent to 5 in mod 7. So both of those numbers are having a remainder of 5. 5 itself has a remainder of 5 when you divide by 7. Also, just for convenience, when you're writing multiple congruences on one line or in one problem, you can just write mod once at the very end of your problem. So, this mod 7 can successfully refer back to all of the congruences, just for a little extra convenience in our notation. And also, with this convenience, we do have to be a little bit careful. If you're switching from different mods in the same problem, then it becomes very important to clarify which mod you're in for which congruent symbol you're looking at. Okay, so one remark to add to this: anytime you have mod m, if you take m itself, it's always congruent to 0. So another way to think of 0 in mod m is all the multiples of m. So if you're working in mod 7 like we were above, every time you see 7, it's the same as 0. So next we're going to do some adding, subtracting, and multiplying. Notice that this sentence doesn't say anything about dividing. We'll get to a replacement for division later on in our coursework, but for the moment we'll just discuss adding, subtracting, and multiplying. How do we do this? Well, you can do this the same as you do with regular numbers, but it's probably much better to reduce first before you do the operation. You could do it either way, before or after, but why not make the number smaller first? Like if we were going to deal with 35 with multiplying, adding, or subtracting, particularly multiplying, it would be a lot nicer to just multiply 5 as opposed to multiply 33. So my recommendation is when adding, subtracting, and multiplying in modular arithmetic, reduce first. Make the number smaller, find the remainder. Or if you want, you could even use negative numbers as well if you prefer to go that direction. Okay. Let's try some calculations in modular arithmetic. So if we have 5 plus 12, we could just do this normally as 5 plus 12, or you could just take the number 12 and subtract the mod. Remember, minus 7 doesn't change anything in mod 7, so we can subtract from 12, 7, and we just get 5 again. So from that we'd get 10, and then from the 10 we could take away 7 again, and that would tell us that 5 plus 12 is actually congruent to 3 in mod 7. Okay, in the next example, we'll try to make use of your reducing first. It's nice to think of a multiple of 7 that's close to whatever number you're dealing with. So if we have 50, how about we subtract 49? And if you have 73, how about we subtract 70? So this would give us 1 plus 3, which is 4 in mod 7. Okay, for the next one, we've got 2 minus 48. 48 is kind of close to 49, and you can also add just like you can subtract. So we could add 49. So that would give us 2 plus 1, which would be 3 in mod 7. So we're finding all of the remainders of these results. Okay, and the next one we have 12 times 16. So in this problem we can really make use out of doing this in our head and reducing first. So instead of doing 12 times 16, we certainly want to reduce, subtract 7, and from the 16 we can subtract 14. So we would end up with 5 times 2. That's 10, which we already discovered above is 3 in mod 7. Okay, in the next example, we could subtract 700 from each one of those numbers instead of multiplying. So you would get 1 times 2 times 3 times 4, or 24, which in mod 7, if we subtract 21, that would reduce to 3. So that covers us for the basic ideas of adding, subtracting, and multiplying. You can do it like normal, just recommended to make the numbers smaller first. What about dealing with powers? What if we have some really big number, like let's take 222 to the power 222. Okay, so if we have to deal with this, what we can do is first reduce the base. So instead of multiplying 222 by itself a whole bunch of times, we'll just take 222 and reduce it to 5 in mod 7. You could use 5 as your base, like 5 times 5 times 5 a whole bunch of times. Or if you like, you could do minus 2. How about we use minus 2? So what we need to do is look for a pattern when we're continually multiplying minus 2 by itself in mod 7. So let's start. Minus 2 raised to the power of 0 would be 1. Minus 2 raised to the power of 1 would be minus 2. Minus 2 raised to the power of 2 would be 4. Minus 2 raised to the power of 3 would be minus 8. And instead of continuing with minus 8, let's add 7 to get minus 1. So minus 2 to the power of 4, we could take minus 1 and multiply by minus 2 to get positive 2. Minus 2 to the power of 5 would be 2 multiplied by minus 2, so minus 4. And then minus 2 to the power of 6 would be minus 4 times minus 2, which is positive 8. Or in mod 7, let's just remember that we're working in mod 7, so I'm going to put a little mod 7 at the end of my problem over here. That would reduce to 1. And notice that we found a pattern. We've got a 1 and then another 1 that appeared. So as we continue taking powers, we'll continue multiplying by minus 2, and this pattern will repeat over and over and over. Notice that this pattern is repeating in a loop of 6, because there's 1, 2, 3, 4, 5, 6 numbers, and then the repeating would start. At this point, it would go again as we count up our powers: 1, minus 2, 4, minus 1, 2, minus 4, on and on and on. So what we need to do is think about, well, what happens when we get all the way up to 222 in the power? So once we get that high, then we're interested in what happens with this loop of 6. So now what we want to do is calculate 222, the power. Maybe we should color code this. Yeah, so this is the 222 coming from the power. We're interested in what is that in mod 6. So if we take 222 and we divide it by 6, there's no remainder. That's a multiple of 2 and a multiple of 3, so that's 0. Okay, now we ended up using 2 mods in my problem, and I want to be really careful about what's a mod 7 and what's a mod 6. So I'm going to come back here and clarify that all of these congruences there were in mod 7, and maybe I'll write mod 7 over here to clarify that those ones were in mod 7 as well. Okay, so what does that mean for our final answer? Well, it would correspond to the part of our loop that has 0 as the remainder in the power, which is this part of the loop where we have 2 to the power 0, and then we go 6 more times, minus 2 to the power 6. So this part here and this part here represent our answer. So I'll get the green pen back out and just note that now that we know that it's 0, then it points to our answer of 1. So final answer 1 is the remainder that we're looking for. Okay, so next we're going to do some word problems in modular arithmetic.